Welcome to Mr. Sweeney's AP Physics C class. This video we're going to be talking about masses on springs and pendulums. And this is part of our oscillation notes. And we're going to start today talking about masses on springs. And a mass attached to a spring is an example of a simple harmonic oscillator. Remember, simple harmonic motion is the periodic motion of something moving back and forth that follows Hooke's law. So obviously a spring, which is a great example of something that follows Hooke's law, would be a great example of a simple harmonic oscillator. The mass on the spring gives it the momentum and the motion it needs to do the oscillations. When we're looking at the oscillations, the most significant thing for any spring system is being able to find the period of the system based on a spring constant and a mass. And we have the equation, and this shows up in your AP Physics C reference tables, which is the period of a spring is equal to 2 pi multiplied by the square root of m over k. Please recall from earlier discussions that when we talked about period, we can look at period as 2 pi divided by angular speed. So in this equation, what we're really looking at is a relationship to look at. Instead of angular speed being related to the period, we could take a look at a combination of both the mass and the spring constant. With that being said, if we're looking at the angular speed, we could always relate the angular speed that's happening for the spring to the spring constant and mass. Angular speed referring to how many oscillations it undergoes per second. And in this scenario, please note that the spring constant is in the numerator and the mass is in the denominator. That is different than what we saw in the previous example where mass was in the numerator. This is because in that last example everything was multiplied across the numerator. It would really be 2 pi divided by angular speed. So we take the inverse of the square root of m over k in this scenario. That's what's equal to angular speed, and that's where we get this equation. If we're looking at the energy in the system, we can reference this energy of any mass system from the equation energy equals 1/2 k x max squared. This is the same equation that we have for the potential energy in the spring, and the idea here is pretty simple. If you're looking at the maximum displacement of the spring, that would be where the spring comes to a stop right before it oscillates back in the opposite direction. At that point, all the energy is stored potentially. There's no kinetic energy, there's no relative potential energy from gravitational sources, so the energy in the spring at that juncture is equal to 1/2 k x max squared. These diagrams do a good job of showing how the oscillations that are occurring with the mass on the spring vary. If you look at this top right diagram, here we have a force being placed on the mass from our spring. You can see that it's at position x, and x0 being equilibrium. So the force is pushing us towards equilibrium. If you're looking at this second picture to the top right, here the force from the spring is 0. The only difference is now we have a velocity for that. It has a certain inertia and momentum from the force being placed on it. That force times displacement is going to do work on the mass, giving it some kinetic energy, giving it a velocity. So when it passes through its equilibrium position, even though there's no forces acting on it from the spring, its inertia is going to push it past equilibrium in this location. And we see that in the third picture down right here. It's moved past equilibrium. Now the spring is compressed. It has a force acting in the opposite direction. This is the restoring force that we've talked about. And this restoring force again puts energy into the system. Please note that both the top left and the picture underneath it are both showing scenarios where all the energy in the system is potential elastic. Again, this fourth one is going back for the equilibrium. Here it has a positive velocity. Same velocity as up top. They're maximum at this position. And then we return at picture E, same as picture A. We are at the same scenario. So we've completed one full cycle here. You can see the forces, the restoring forces, which way they're pointing, where the velocities are maximum and minimum. Also note that in pictures A and C, those are the points where the elastic kinetic energy is maximum, or the elastic potential energy is maximum, and then B and D is where the kinetic energy is maximum. So let's do an example of this. In this example, we talk about shock absorbers on a car. They're what keep the car from bouncing after it hits the bump. The wheels are able to move up and down in the tire well. This allows you to hit a speed bump or a pothole, and your car doesn't lurch when you do that. Your wheels bounce, and the shock absorbers that are there, they would oscillate at that time. So what I want to find out is, if we considered all these things ideal, what period and frequency of the car without the shock absorbers, if the car has a mass of 950 kilograms and the springs on the car have a spring constant of 6.47 times 10 to the 4 newtons per meter. So they give us a mass and they give us a spring constant. Well, we're going to put that into this equation. The period of a spring is equal to 2 pi square root of mass divided by spring constant, and plugging in for those values, we have 950 kilograms divided by 6.47 times 10 to the 4 newtons per meter. And when we solve this whole right side of the equation, we get the period of a spring being 0.761 seconds. So this gives us the period. If we wanted the frequency from here, we would just take the inverse of that. So it would be, the frequency would be 1 divided by 0.761 seconds. If we're looking at springs, mass spring systems typically come with one spring, but there are scenarios where we have either two springs connected with a mass at the end of just one of them. That would be a spring in series, series meaning one after another. Or we can have springs that are parallel to each other, meaning that they are literally parallel to each other, holding up the mass. When we're looking at this, what we want to do, the idea is that we want to take this system and represent the combination of springs as one equivalent spring constant. So we still want to treat the system like it's one spring, but we want to meld all the springs with their spring constants as one acting system, and that models the system really well. So for series, to find the equivalent spring constant, we have to add the inverses of the individual spring constants, and that gives us the spring constant totally. Note that when you add inverses like this, you might remember this from when we did electricity, adding inverses will always have the equivalent spring constant be less than any of the individuals. The more springs you add in series, the less the effective spring constant of the system is. So you can manipulate a spring constant of a system by stringing two of them together in a line. That will give you a lesser spring constant effectively for your system. If you're looking at parallel, it's the opposite. You would add the spring constants together to get the equivalent. So these add together. If they're side by side, both pulling on the spring, you'd have to stretch both of them. They don't stretch relative to each other. So if you find them in series, you add the inverses to get the inverse of the equivalent. If they're in parallel, you add the spring constants to find the equivalent spring constant. Alright, so then that brings us to the pendulum. A simple pendulum is a mass suspended from a fixed point that oscillates through a small angle. This is very important, this part about small angle. You cannot have a simple pendulum that has a large angle. There's a little bit of turbulence in the system. It no longer acts as a oscillating system if the angle gets too large. You'll find that all the examples we give you in this class are always at a small angle. In real life, you might have experienced this on a swing. As you get the swing, because that's more or less a simple pendulum, the higher the swing goes, the less the behaviors is predictable. You start to get a little slack in the line when you hit the top. So that can't be. The only way to do that is for the downward force of gravity at small angles always to be the dominant force. So as we go to large angles, there's a little bit of give and a little bit of slack develops in the rope. So simple pendulums must be small angle. If you do maintain that small angle, anything that's from a fixed point that's oscillating due to gravity will act like a simple harmonic motion. And there's only two things that depend on this. We have the string length, or the rope length, the chain length, whatever the length that is. That will impact the period of the pendulum and acceleration due to gravity. On Earth, that's constant. You might find some examples where they might put you in an elevator, or they'll bring you to some foreign planet. That's a little unusual, but just realize that the acceleration due to gravity, or the effective acceleration due to gravity, is going to play a large role on this as well. Our equation then for the period of the pendulum is period equals 2 pi square root of length of the string divided by g. Note the similarities between these equations. The mass on the spring was 2 pi square root of m over k. This is 2 pi square root of L divided by g. The idea is pretty simple. The 2 pi here is representing one full rotation in radians. And then the square root of L over g is just the inverse of our angular speed. Similarly, in the previous equation, the square root of m divided by k was just the inverse of our angular speed. So we're still kind of adhering to that period idea where you have 2 pi divided by angular speed. These are rearrangements of that simple relationship, and they're just tuning that angular speed to be in terms of what we find these systems in. In this case, square root of L divided by g. So let's do an example of this. What is the length of a pendulum that has a period of 0.700 seconds? So that means it takes 0.7 seconds for it to complete one cycle. We're going to use this equation we just talked about, which is the period of the pendulum is equal to 2 pi square root of L divided by g. And plugging in our period, we have 0.7 seconds, and then our acceleration due to gravity, which is 9.8 meters per second squared. Solving for the length of the pendulum, we find that the pendulum length in this scenario must be 0.122 meters. So any pendulum, regardless of the angle that you put it at, regardless of the mass you put on the pendulum, if it's 0.122 meters long, when you neglect friction, it's going to take 0.7 seconds for that to oscillate. Let's try another example. This example, it asks how long does it take a child to swim one complete swing if her center of gravity is 3.5 meters below the pivot. In that case, we're trying to find period. They also want to know what the frequency is. In this scenario, we're using that same exact equation, but now instead of having period, they're giving us length. So if you're 3.5 meters below, which would be one heck of a swing, we would plug that into length, and that would be 3.5 divided by 9.8. You just take the square root of that, multiply it by 2 pi, and you find it has a period of 3.75 seconds. Think in this swing more of like maybe a swing off a tree branch, maybe over a creek or something like that, something that's got a very, very long rope. 3.5 meters is just about a story. To find the frequency of this, we plug into the equation period equals 1 over frequency. 3.75 seconds is the period. We want to take the inverse of that, and that is equal to 0.267 hertz, which is the frequency of our swing. Moving on to our last topic, we're going to talk about the energy in simple harmonic motion. Now, just like everything else, energy in this system is going to be conserved. And for simple harmonic motion, the sum of the elastic potential energy or the gravitational potential energy, if it's, say, a pendulum, and the kinetic energy is always constant. So the energy is always conserved. It just switches between potential and kinetic, back and forth. But if you added the potential and kinetic together at any point, you'd always get the same exact amount of energy. So the potential energy plus the kinetic energy, that is constant. So let's take a look at our kinetic energy equation. This is equal to 1/2 mv squared. Now we've already developed an equation previously for the velocity of an object in simple harmonic motion. You might recall that the velocity is equal to the derivative of our position equation being x max cosine angular speed times t. When you take the derivative of that, it is negative x max angular speed multiplied by sine angular speed times t. So we have an equation for kinetic energy, we have an equation for velocity. We can substitute in for our kinetic energy equation this velocity equation. You're not going to see this in your reference table, this combined, but if you ever need to find the kinetic energy, this would be the method. So here I've just taken my top equation, substituted in velocity for what we saw, and we're going to end up with kinetic energy equals 1/2 k. That's what we see from our previous equation. Then we're squaring everything in our velocity. X max is squared, sine times the phase, which is angular speed times t, that also gets squared. So 1/2 k x max squared sine squared omega t. And that is the equation for that. If you're looking at the potential energy, we have something very similar. The potential energy is 1/2 kx squared. We previously had an equation for position. It's x equals x max cosine omega t. When we substitute this in for our x, our potential energy is 1/2 k x max cosine omega t, and we square that whole thing. This is what we get. Potential energy is equal to 1/2 k x max squared cosine squared omega t. Notice the similarities between these two previous equations. It's both x max squared, it's both sine or cosine squared omega t, 1/2 k or 1/2 m. So they take very similar forms, which really makes sense when you think about energy. All right, looking at damped harmonic motion. Up to this point, everything we've talked about with energy in simple harmonic motion has been looking at frictionless system. It's acting like there's not air resistance in the way. It's acting like there's no friction between surfaces. We know that not to be true. We look at things in their ideal state because it really tells us what's trying to happen. But in reality, most everything that we have in our environment is subject to friction. When you talk about friction in simple harmonic motion, the proper word for that is damped or dampened harmonic motion. So if you ever hear something talking about something dampened, what they're talking about is something that should be oscillating, but its oscillations are decreasing. Think of anything that's ever vibrated, and if you were to kind of say like the vibrating string on a guitar, if you were to touch your finger to the vibrating string, it would stop making its noise and the string would stop vibrating. That's dampening. Dampening is taking energy out of the system. So dampening causes objects in simple harmonic motion to decrease their amplitude, their motions, and eventually come to rest. Dampening doesn't necessarily change the period of the oscillation. It could, depending on the system, but dampening, what it always does is decrease amplitude. That is the most appropriate way to look at damped motion. So here's some examples of damped harmonic motion. The first one being shocks in a car. We talked about how your cars have springs on them. The springs keep you from bouncing when you hit a pothole or say like a speed bump. But we need to dampen those springs because otherwise when you went over that bump, your car would be constantly bouncing. So every suspension in the car is made up of two systems. One, you have a spring. The springs keep you so that way your tires and your wheel well can oscillate when they go over bumps. And then you have shocks. Shocks are what dampen your springs. Another example would be a pendulum or a mass on spring coming to stop. The thing dampening here is looking at air. So usually friction and air will bring those things to a stop. And again, I already used this example, but another example would be a guitar string coming to a rest. We actually see a lot of dampening in different scenarios, everywhere from the things that hold our doors open to our cars. Dampening is something that happens naturally in our environment, but we also look to dampen things for certain purposes. If you look at earthquakes, buildings are dampened so that they do not resonate and cause catastrophic failure. That'll finish up our notes on oscillations. We do have our test coming up on Thursday, and that's it.